Hello all, welcome back to my YouTube channel all about VLSI. Hope you are all doing good. I hope my voice is audible and my screen is visible. So let's start today's session. Give me 1 minute. Yeah, give me 1 minute. I'm opening my PPT. Yeah, so let us start our session. I hope my voice is audible and my screen is not yet visible. I will share my screen. So in previous session we have completed with the discussion of addition and subtraction using one's complement and as well as two's complement, right? That we have discussed in previous session. So in today's session we will start with the discussion of binary coded decimal, gray code and XS3 codes in digital. Okay, so what are these BCD codes and gray codes and XS3 codes that we will going to discuss in this session. Okay, so we will start our discussion with BCD codes. So let us start with the topic called BCD codes, which stands for binary coded decimal numbers. Binary coded decimal numbers. So BCD stands for binary coded decimal numbers. So the binary coded decimal numbers is a type of binary codes used to represent a given decimal number in a equivalent of binary form. So this BCD are used to represent decimal numbers in binary form. So the BCD equivalent of a decimal number is written by replacing each decimal digit in the integer and fractional part with its 4-bit binary equivalent. So each decimal digit is represented in 4-bit binary form. Okay, so each decimal digit is represented in 4-bit binary form. This is very important. Okay, so each decimal digit, whether it may be integer or it may be a fractional part, will be represented in 4-bit binary form. Okay, so the BCD code for the BCD is only valid for the decimal digits 0 to 9. Okay, so the BCD is only valid for 0 to 9. So what is this? I will show you now. Okay, so for the BCD code for the decimal number 0 is, so it should be represented in 4-bit binary form 0 0 0 0. So this is the BCD representation of 0. And coming to 1, it is 0 0 0 1. 2 is 0 0 1 0. 3 is 0 0 1 1, followed by 4 5 6 7 8 and 9. 4 is nothing but 1 triple 0, 1 double 0 1. 6 is nothing but 1 0 1 0. 7 is nothing but triple 1 0. 8, sorry, this is 4, right? Sorry, it is nothing but 0 1 double 0, 0 1 0 1, 0 1 1 0, 0 triple 1, and 8 is nothing but 1 triple 0, and 9 is nothing but 1 double 0 1. So these are the representation of BCD. Okay, so we can represent the BCD of each decimal number in 4-bit binary form. Okay, so the BCD numbers for 0 to 9 are given here. Okay, if we want to write the BCD for the number 10, we have to represent each decimal digit. Okay, so we have to write the binary form for each BCD form for each digit. So for the BCD form of 1 is 0001 and 0 is 4 zeros. So this is the representation of decimal number 10 in BCD form. Okay, so this is how we are going to represent the BCD form of 2-digit numbers, that is from 10 to 99. And if it is 3-digit number, again we have to represent each and every decimal digit in its binary form. Okay, so if we have let's say 153, then we will represent this as 0001. 5 is nothing but 0101, and 3 is nothing but 0011. This is how we are going to represent the BCD number of a decimal number. I hope it is clear, right? Now, so there are basically 6 invalid codes. There are basically 6 invalid codes. 6 invalid BCD codes, which are nothing but 1010. This is invalid. 1011 is also invalid. 1100 is also invalid. 1110 is also invalid, and 4 ones is also invalid. Okay, so these are basically invalid codes. We cannot directly represent 10 as 1010. No, this is wrong representation. We cannot represent 10 in BCD as 1010. We cannot represent, this is wrong format of BCD, and we cannot represent 11, that is B. So if we want 11 to be represented in BCD, you cannot represent 1011. No, it is not correct. Okay, so the BCD is nothing but we have to write the representation of each and every single digit. We have to write 0001 followed by 0001. This is the BCD representation of 11. Okay, this is the binary representation, not the BCD representation. So that's why this is an invalid. And similarly, so these are all the invalid cases. Okay, so there are how many cases? There are basically 6 invalid cases in the BCD representation. Okay, now how to convert any BCD number into a binary number? So how to convert a BCD to binary? So how to convert any BCD number into a binary number? What is the process? So if a BCD number, let's say 10100010 is given to us, and if we want to convert this BCD number into a binary number, then how can we convert this BCD number into a binary number? So first we will follow, so first we should convert BCD to decimal. So we have to convert the number from BCD to decimal. Then we have to convert the decimal number into a binary number. Then we have to convert the decimal number into a binary number. This is the process we should follow. So how to convert any BCD number into a binary number? First we have to convert this BCD number into a decimal number, and then we can convert the decimal number into a binary number. How? Let's say here we have 10100010. So what is the decimal equivalent of this particular binary BCD number? So 1010 is nothing but A. Okay, 1010 is nothing but A. But is it a valid? But is it a valid code? No, right? So there is no representation of BCD. So this is invalid. Let's say 10000010 0010. Okay, now it is nothing but 8 followed by 2. So the BCD, so the decimal representation of BCD number is 82 to the base 10. Okay, so it is nothing but 82 to the base 10. Now we will convert this 82 to the base 10 into a binary number. The process we know already. 82 repetitive division. 2 times 4, 2 times 1, remainder is 0, 2 times 2, 2 times 0, remainder is 1. Okay, 10, 0, 5, 0. So like this, by the repetitive division, you will get the binary number. So the process is important here. We will convert the BCD number into a decimal number, and that decimal number we will convert it into a binary number. So that is how we are going to convert any BCD number into a binary number. Okay. Now, let's say if we have a binary number 1 0 1 1 0 1 0 1 0. Okay, this is what we are having. This is a binary representation if we have given. Okay, so how to convert it into a BCD? So the first step is to convert this binary number into a decimal number. So we have to convert this binary number into a decimal number. Then we have to perform decimal to BCD conversion. Then we have to perform decimal to BCD conversion. So that is how we are going to convert a binary number into a decimal number. So if we want to convert a binary number into a decimal number, if we have to convert a binary number into a BCD number, first we have to convert the number into decimal, and from decimal to BCD. So this is how we are going to convert a binary to BCD number. Okay. Now, let us discuss BCD arithmetic. So in the BCD arithmetic, we have BCD addition. Let us see how to perform this BCD addition. So in BCD addition, each digit or a decimal number is converted into a 4-bit binary equivalent, and the addition of two BCD codes is performed using the basic rules of binary addition. So first step is to convert the decimal number into, so if a decimal number 15 plus 4, okay, let's take simple case. Let's have 4 plus 4 is equal to 8. So we have to perform the BCD addition on these numbers. Okay, so we should convert this 4 into BCD form, which is nothing but 0 1 0 0, and 4 is nothing but 0 1 0 0. So this is BCD representation of these two decimal numbers. So we have 0 1 0 0 0 1 0 0, and we will add this 0 0 1 1 0, carry 1 1. So what is our final answer? It is equal to 8. Now the final answer is less than 9. Okay, so since the final answer, I will write it here, if the result is less than 9, then it is a valid BCD number. Else, if the result is greater than 9, or if a carry is generated from the 4th bit sum, the sum is invalid. That is, if we get a carry here, then the sum is invalid. Okay, so let's take this example, 5 plus 5, which is equal to 10. So what is the representation of 5? Which is nothing but 0 1 0 1, and again 0 1 0 1. So if we add this, 1 1 0 1 carries 1 1 1 1 0 1. Okay, and we have 1 0 1 0, which is greater than 9. Okay, so this result is invalid. So this is a invalid result. Okay, so this is a invalid result. So how to make it to valid? So we have to, we are going to add 6. So we should add 6 to the sum to make it a valid BCD number. So if the final result is an invalid result, then we have to add 6 to make it valid. So 1 0 1 0 plus 0 1 1 0. The final result will be 0 1 1 0 1 1 1 0 1 1 1 0 1. The carry will be discarded. Okay, and the carry will be discarded. It will be sent to the next group. So this is how we are going to make the final result into a valid BCD code. Okay, so this is the process of BCD addition. Okay, now similarly, if we want to perform BCD subtraction, BCD subtraction. How to perform BCD subtraction? If you want to perform 5 minus 6, okay, so 5 minus 6 can be performed. How we can perform this 5 minus 6? 5 minus 6 is nothing but 5 minus, or you can say 5 plus 9's complement of 6, or 5 plus 9's complement of 6. Sorry, 10's complement of 6. So instead of subtracting directly, you can find the 9's complement of 6, or you can find the 10's complement of 6, and after finding the complement you can add it with the number 5. Okay, so if the result is greater than 9, then the result is invalid and you should add 6 to make it a valid. And if a carry is generated in the result, then also we are going to add 0110. Okay, so this is how we are going to subtract two numbers, BCD subtraction. Okay, so this is about BCD code in our digital. Okay, now the next type of code we have is XS3 code. XS3 code. What is this XS3 code? Any idea? So basically, this XS3 code of a given decimal number is determined by adding 3 to each decimal digit. Okay, so XS3 code of a decimal number is given by adding 3 to each decimal digit in the given number and then replacing each digit of the newly found decimal number by its 4-bit binary equivalent. For example, if we have a decimal digit 0, okay, what is the XS3 code of this decimal digit 0? First we should find it into binary. First we should convert it into binary, that is 0 0 0 0 in 4-bit form, and we have to add 3. Okay, 0 0 1 1, so the result will be 1 1 0 0. So for 0, the XS3 code is 0011. So this is how we are going to find the XS3 code of a decimal number. So this is how we are going to find the XS3 code of a decimal number. So if we have a decimal number, let's say 4, okay, so how to find the XS3 code of this decimal number 4? First we have to write it in a 4-bit binary form, which is nothing but 0 1 0 0, and we have to add 3, which is nothing but 0 0 1 1. So final result will be 1 1 1 0. So this is the XS3 code for our 4, decimal 4. 4 is nothing but 0 111 is the XS3 code. So if we write like this, so for 0 it will be 0 0 1 1, 1 it will be 0 1 0 0, 2 will be 0 1 0 1, 3 it will be 0 1 1 0. Like this we have up to 9. So on 9 we have 1100. So these are the XS3 codes of our decimal numbers. Okay, is this clear? And if you observe carefully, XS3 code also have 6 invalid states. XS3 code also have 6 invalid states. What are those? Which is nothing but 0 0 0 0, 0001, and 0 0 1 0, and 1 1 0 1, 1 0, and 4 ones. So these are the 6 invalid case states in the case of our XS3. So these are not present in our XS3 representation. Okay, I hope this is clear. Now let us start with another type of coding, which is called as gray code. So gray code is also a 4-bit numeric code. It is a unit distance code. It is a unit distance code. Why it is unit distance code? We will see in a minute. Because successive code words in this code differs in 1 bit by position. Okay, and it is also called as a reflective code. And it is also called as a reflective code. So gray code is also called as a unit distance code and a reflective code. So let us see the representation of gray code. So for 0, decimal 0, the gray code is 4 zeros, and for 1, the representation is 0, 0, 0, 1, and 2, decimal 2, the gray code is 0, 0, 1, 1, and 3, it is 0, 0, 1, 0, and 4, 0, 1, 1, 0, 5, 0, 1, 0, 1. This is gray code representation. Okay, not binary. It is gray code representation, and this is a decimal number. And 6, we have 0, 1, 0. Sorry, 5 it is 0, 1, 1. 5 it is 0, 1, 1. Can you observe anything in the pattern? So basically here, if you observe the LSB, for 0 it is 0, and in the case of decimal 1, the LSB is changing to 1, and no other bit is changing except the LSB bit. And for 2, if you compare 1 and 2, you can observe the LSB is same, every bit is same, only the last but one bit is changing. Okay, and if you observe 2 and 3, the last but one bit is same, but the LSB is changing, and all other bits remains the same except the LSB. So if you observe, if you compare two numbers 0, 1 or 1, 2 or 2, 3, only one bit is changing. Only one bit is changing. So this is what that is what it is called as unit distance code. Why it is called as unit distance code? Because only one bit will change from one decimal number to another decimal number, successive decimal numbers. So between the successive decimal numbers, only one bit changes. Okay, so this is how we can write up to F. So 0 to F, we can write the gray codes by changing only the single bit, by only changing the successive single bit in the successive numbers. Okay, now how to convert binary to gray code. So how to convert this binary to gray? What is the process? So the most significant bit MSB of the equivalent gray code is same as MSB of binary bit. So let us say a binary number 10110. This is a binary number, and we have to convert it into gray. So the MSB remains the same, and from the next bit we have to XOR the successive bits of the binary number. So we should XOR 1 and 0. So we have to XOR the successive bits of the binary number, and the result will be written in the gray code. So 1 XOR with 0 is 1, and 0 XOR with 1 is 0 XOR with 1 is 1, and 1 XOR with 1 is 0, and 1 XOR with 0 is nothing but 1. So this is how we are going to find the gray code of a binary number, right? So this is how we will convert a binary code into a gray code. If you are not aware of XOR operation, don't worry, we will discuss in our upcoming sessions. What is meant by this XOR operation, we will discuss. Okay, yeah. Now, next, how to convert gray code to binary code? How to convert this gray code to binary code, vice versa? How to do that? Any idea? So let us take one gray code 1 1 0 1 1. So this is a gray code, and we have to convert it into a binary code. So the MSB remains the same, and from the next bit we have to crisscross. We have to do the XOR operation in a crisscross manner. So the binary of MSB will be XOR with second bit of gray code, and the result will be stored in the binary. So 1 XOR with 1 will be equal to 0, and 0 XOR with 0, and the result will be stored here, which is nothing but 0, and 0 XOR with 1 is nothing but 1, and the result will be stored in the binary, and the 1 XOR with 1 is nothing but 0. So this is a binary representation of the gray code, 11011. So this is how we are going to convert a gray code into a binary code by following the crisscross manner. Okay, so this is the process of converting gray code to a binary code, right? I hope this is clear. So this is how we are going to convert binary to gray and gray to binary. Now, so this is about the BCD code, that is binary coded decimal, and gray codes as well as XS3 codes in our digital. Okay, so I hope this lecture is clear, and so that's all for this session. So if you like this session, please like, share, and subscribe to my YouTube channel all about VLSI. Yeah, so if you're having any doubts, you can ask me, or you can also comment in the comment section. I will try to help you. Okay, so that's all for this session. Thank you. Good night.